Sir Kannan Gopalakrishnan. He was working as a senior architect at Engineering Design Research Centre, L&T Construction, India's largest construction company. He's also worked on projects ranging from institutional buildings to international airports, apartment complexes to aircraft hangars. He's also attended 3 international conferences and 2 national conferences, and has also presented technical papers at the Jawaharlal Nehru University, Delhi, and the MSRIT, Bangalore. He's also won the national championship at Archaman at the India's largest architecture quiz. Sir Kannan Gopalakrishnan currently runs a design firm, Habitat Design Studio, and he is also a visiting faculty at the renowned architecture schools in Tamil Nadu.
Welcome back to UGC lecture series. This is AR 6006 Structure and Architecture. We are doing units 3 and 4. We are dealing contemporary structural expression through case studies. This is lecture 16, and if you could kindly remember the previous lecture, we saw very interesting buildings such as the Fleet Guard, the Pat Center, Princeton, the Olympic Athletic Center of Athens, 2 of them designed by famous architects Richard Rogers, and the last one designed by famous architect again, Santiago Calatrava. Today we are going to look at one very interesting case study, which is the Kansai International Airport Terminal building. Kansai International Airport is an international airport located on an artificial island in the middle of Osaka Bay. An artificial island. What do they even mean by an artificial island? Yes, they scooped the sea out of a bay, they created an island, they started building an airport in the island. This is the map of Osaka Bay, and if you could see here, this entire thing was the Bay of Osaka, and this right here is the city of Osaka. The airport of Osaka was getting very small, and since the airport is within the city, the operational hours could not be made 24/7. To increase the air traffic, to ease the congestion of air traffic in Osaka airport, the need for a new Osaka airport was understood in 1960s. So what they did was they started looking for alternate locations where they can start building a new airport. Without going anywhere, they found that the best way to build an airport without getting too far away from the city is to build the airport as close to the city as possible. At the same time, they should have enough land, such a big area of land, to develop an international airport. To develop an international airport, you would require a land of at least 3 km by 1 km area to lay out big runways and great passenger terminal buildings, to handle air traffic control towers and a lot of other subsidiary ancillary structures. You need a very big area. So what the people of Osaka decided was they will scoop out of the sea and build an airport. That's exactly what they did. If you look at the map here, this entire thing was the Bay of Osaka, and this here, right here in the far right corner, is Kansai International Airport. This entire island is created inside the sea by breaking in 3 huge mountains and placing it onto this location. This is accessed by a road that leads from Osaka. This is only access to the airport. This is the runway and this is the passenger terminal building. If you want a closer look, let's take a look at this. This is that road that connects airport terminal with the main city of Osaka. Here you have the airport terminal. It looks like this, and this right here is the main runway. The building has a single 4-story terminal designed by Renzo Piano Building Workshop. It is the longest airport terminal in the world at a total length of about 1.7 kilometers from end to end. A sophisticated people mover system called the wing shuttle moves passengers from one end of the pier to the other. The terminal is 1.7 km long with 42 boarding gates designed to handle 1 lakh passengers per day. Its long and light structure is designed to withstand the violent earthquakes which often affect this region of Japan. Below there is the conceptual sketch of the airport, which was done by Renzo Piano. This is the terminal building that he had designed, and this is the reclaimed land. Kansai Airport rests upon the island like a glider seen in plan. The main body of the airport forming its fuselage, the boarding gates positioned in its wings. A notable feature and one of the primary importance in the organization of an airport is the unobstructed visibility of the planes themselves, thanks to the uninterrupted lines of vision through the open departure level at the main terminal building. The departure level is covered by a large clear span, undulating roof of asymmetrical form. It is perhaps the shape that is the project's main innovation. The form of the roof came from extensive study of structural and ventilation requirements undertaken with Peter Rice and Tom Barker from O. Arup structural and services engineers respectively. This is the look of the building. The sketch that was designed by Renzo Piano. Look at the sketch, and let's compare the sketch with how the building has transposed here. It was decided that the air could simply be projected across space from the rear of the building towards the front, that is the runway side. It is this predicted trajectory of air that is mimicked in the form of the roof we see today. Having thus avoided enclosed air distribution ducts suspended from the ceiling, the vast structure is left exposed. What happened was, they understood the fact that air can simply be projected from one place to another just by curving a structure, and just by the curvature of the structure, just by the physics of the structure itself, the air will tend to move from one end of the building to another end of the building, that is from the rear of the building where there are strong wind currents to the front of the building near the runway side. So, you can see curved panels on the building's interiors. Thereby, what happens here is, usually in a airport building there are huge air diffusers and air distribution ducts which obstruct the view of the entire airport terminal. So, in this case, when the draft itself is moved from one end of the building to another end, this can be avoided altogether. Beneath, blade like deflectors serve not only to guide the airflow, but also to reflect the light coming in through the skylights on the roof. You can see these huge trajectories of air moving across the building. You can see through these structures. There is a better picture, I will explain it coming slides. Let us take a look at the structural design of the system. We saw large number of suspension buildings in the earlier episodes. Now, it is time that we see something very solid. So, let us look at solid steel structure. Airport buildings nowadays use solid steel structuring. They call it the tubular truss. The tubular sections of steel which brace each other, forming truss like structure, thereby supporting the entire weight of the airport. This is the modern day structural equivalent for an airport design. In the main terminal building, the geometry of the roof's undulating cross section is formed of a series of arcs of different radii connected at tangent points. Three-dimensional beams spanning 80 meters follow the cross-sectional asymmetrical form of the roof, supported at their extremes by pairs of inclined columns. The 42 boarding gates are housed within the wings of the glider. You can see these tubular trusses which go through the entire end, and look at how long the building is. You cannot see the end of the building in this area, because that is how long the airport is. It is about 1.7 kilometers long building. Their glazed facades address the runway, while their opaque curved roof sweep down to turn its back on the distant coastline. The height of the wings decreased to the building's extremities, with the roofs following an almost imperceptible curve, just sufficient to ensure the control tower's lateral line of vision. In any airport, the control tower is one place from which you must have unobstructed vision to the entire airport terminal. So, from the control terminal, you must be able to look at every spot of the airport. None of it should be obstructed. In some cases, the building itself can obstruct some portions of the space which goes unobserved by the control tower. So, just to minimize that, what Renzo Piano has done in this building is he has taken a huge torus toroid of a diameter of 42 kilometers, and then he has used one portion of a toroid, which is what makes the structure. What it means is, at the ends of the building, the height of the building is low, and at the middle section, the height of the building is huge, which gives the control tower enough view across all the places, unobstructed view across all the places. Geometrical studies led to the development of a mathematical model that would guarantee the maximum standardization of components for the building. Maximum standardization of components. Why is standardization required in an airport building? Because since this is an offshore project and you have to necessarily make the components elsewhere in a factory fabricated at some other environment in the city, you cannot make it in the middle of the sea. So, you have to get it done from an off-site facility, manufacture it, transport it via ships, and get it to the site and then assemble it. So, the standardization of components becomes entirely critical because you cannot have n number of components in your building. The number of components needs to be minimized so that the manufacturing costs and transportation things are becoming very easy, because to transport a large number of items, you have to think about transporting each different kind of item separately, packing of each different item, lifting, the way in which you put the hooks onto the thing and then lift it, everything differs. So, if the number of components are minimized, the way you transport the structure, the entire speed of construction is very fast, and you can end the project on time. The final result of all the standardization is that all of Kansai Airport's 82,000 stainless steel panels of the roof are absolutely identical. This is also because thankfully the building's overall size, which allowed the curves to be absorbed with low tolerances. The building is so huge that even a curve looks like straight line in that scale, because if the panels are about this big, the panels in a curve that is so big does not look like it's a curve. It looks like a straight line, and the overall picture, when you look at the building itself, does not look like a series of straight lines formed by panels. It looks like one continuous curve. So, that is the advantage which the size of the building itself gave to the architect. Kansai International Airport is the world's first airport which is built inside the ocean. Soon after opening, 4 months after opening, there was this massive earthquake in Kobe, of the magnitude of about 6.7 on the Richter scale. The airport survived with very minor damage, and it also provided continuous transportation and operation during the entire course of relief effort, which is very amazing, because the greatest challenge in this particular project is to build an airport terminal inside the sea. Human beings, we have evolved the study of architecture, constructing buildings on land. This building proved a very different course, charted an entirely different course in the career of in human architecture, because we started building on water, literally, but we built on land, but still the land which we built on is actually surrounded by water, and still now we hadn't encountered that kind of a force system which the water thrusts on the land. Annually, the entire island of Kansai goes down by a certain number of centimeters every year, because it has been built on compacted soil and mud and earth. So, there are people who are working on limiting this kind of a system as well, but as we speak, this is one of the marvels of engineering, that we have achieved so far in architecture itself. Look at the structural system of the building, tubular trusses which we were talking about, and in this space we can clearly see the curved areas which divert the wind from one end of the airport to another. These are curvatures through which the air gets sucked in from one side, it gets transported and then it's delivered onto the other side, leaving the entire airport without the need of any air transmission or any air conditioning diffuser systems. This is that toroid which I was talking about. The entire airport terminal is made in the form of a very big toroid with a diameter of about 42 kilometers, but we didn't use the entire structure, but because the entire structure will be under the sea, we didn't use the entire structure. They used only 1.7 kilometer portion, which is just the top of this portion, just to make sure that the height of the building at this level is small and the height of the building at this level is little big, just so that the air traffic control can look at all the paths with relative ease. That is why this curvature is there, and this curvature is practically not visible at all until you actually take a very close look at it and see this curvature is not practically seen. We saw one of the earlier sketches of Renzo Piano in which he tried to get the form of the roof, and this is that long corridor which we saw the pictures, and this is the main passenger terminal building. And look at how this section has been realized in actual real building. We spoke about this in one of the earlier lectures, and I was wondering about how famous architects are able to do this at very experienced level, because they are able to perceive the entire building so much so much advanced level that they can immediately sketch out the form of the building, they can immediately sketch out what the building must look like, and they are able to realize exact same way which they had sketched it. And if you could look at the picture, you can clearly not tell any difference between the sketch and the thing itself. He has got everything that he wanted. He wanted the X-shaped escalators, and he's got the escalators, and he wanted support over here, and he got the support over here with a column, and he's got supports over here and continuous escalators in different levels. He's got 1, 2 and 3 levels. He's got the levels here. Practically he's got all the things that he wanted in the concept, in the actual plan. And this is a detailed section of the Kansai International Airport, and due to the paucity of space in the slide, I have broken down the thing into two things, and it is actually one continuous airport. And this is the place where the air gets sucked in from one end of the terminal, and it gets transformed to another end of the terminal and gets deposited over here. And there is a space in which, between the two curves, in which there are exit points for the air to get out and get in. So, air clearly moves between these points, so that the entire terminal is, you do not require any air throw material over here. This is the overall plan of the terminal, and this is the terminal building. This is the runway. This is how you get inside the thing. The Osaka city is somewhere on here. This is, all these are water lines. This is how you enter the airport, and drop off, parking, ancillary structures and other buildings. You enter the building, passenger terminal building. These are the different gates, the 42 gates which they were talking about, and airplanes placed all around. So, the planes can take any of these routes and get onto the runway, and then they can move. This is the circulation of the airport, and if you take a section across this bay, this is how it looks. You have the passenger gates. This is the transit system that they were talking about, which travels people from one end to another end, and these are the escalators through which they can come to this level where the escalators that travel them from this transit thing to the aircraft belt. Another look at the airport terminal. The sketch that Renzo Piano sketched is right here. This is the main passenger terminal building, and these are the 42 gates. And this is a space in which aircrafts can be parked, and people can board the aircrafts on. These are the gates, and this is the transit system which moves passengers from one end of the airport to another end. This is another view of the airport itself. Japan is the land of rising sun, the easternmost country in the world, and you can see that right here. It is noteworthy about the size of the island which they have excavated here. It's 1 kilometer by 4 kilometer island, which has been, not excavated, land filled, and built an entire airport building on the sea. Another view of the building. Here you can clearly see the stainless steel panels on the roof, clearly distinguished. Here it says Kansai next to the runway. The primary structural element is a truss here, a tubular truss, which is a Warren truss. This Warren truss looks like this. It's a triangular 3-dimensional truss. It's asymmetrically arched, shaping in the shape of the curvilinear roof on the top, because the truss travels from one end of the building to another end, from here till here, and it is supported at 1, 2, 3 locations, and this traces the line of the roof over here. If you consider this to be one truss, there are totally 18 trusses which are placed exactly 14.4 meters apart. If there is one truss here, and after 14.4 meters there is another truss next to it, and there is another 14.4 meters apart, there is another truss next to it. In that case, each truss is spanning a distance of about 82.8 meters. From this end to this end, it spans a distance of 82.8 meters. There are a series of continuous secondary structures, which are these structures that you are talking about here. Continuous secondary trusses which spans across the primary trusses, built out of I sections and traditional cross bracing. These are the primary Warren trusses, and these are secondary trusses which you see over here, built out of I sections and traditional cross bracing. You can see the regular conventional cross bracing that they have. These are designed to absorb lateral forces generated by earthquakes. There are very many different types of forces which play in an airport building. When a building that is as large as an airport building, the primary force is the axial force, which is generated by the dead load and the load on top of it. Wind load, you never know from which direction wind is going to attack, so wind is a lateral force. Similarly, earthquake again is a shift in Earth's plate, which means the force is going to be lateral, horizontal. So when the horizontal lateral force hits the building needs to be strong enough to withhold large forces, and being located in Japan, it is absolutely essential that the building holds very, very strong earthquakes, because Japan is situated in a highly earthquake prone zone, and earthquakes are very common there. And just as we saw in the earlier part of this very episode, the airport saw a massive earthquake of about 6.7 Richter magnitude after only 4 months of inauguration. And these are the secondary trusses which we were talking about. The secondary trusses have another duty. They also must help the primary trusses when they try to buckle. Because of the enormous span, when the primary truss tries to buckle, these are the secondary trusses, or secondary structural elements are the ones which tries to stop the primary trusses from buckling. Since the building is about 1.7 kilometers long, and every material that we know of expands when heated up, contracts when cooled down. So when there is expansion, if the material starts to expand in different directions, there might be undulations, and it might also lead to fatigue of elements, and there might also be a fracture of elements and it might cause a collapse. So, expansion joints have been allowed for in the design. Expansion joints of widths of about 450 to 600 mm thickness are allowed for in the design of the building every 150 to 200 meters, and this gap is filled by rubberized elements to provide weatherproofing in such a way that water will not get inside between these gaps. We have come to an almost end of the episode, in which we will try to understand what we learned in this episode. We should have understood the importance of structural expression in contemporary architecture through understanding of complex architecture structures such as Kansai International Airport. We would also try to understand the working genius of architects and great minds like Renzo Piano. With the information that we've just got from this lecture so far, we should be able to answer this single question that's going to appear on your screen right now. Explain the Kansai International Airport project with reference to its unique locational importance and how the architect averted disaster by simply following physics. I look forward to meeting you with more case studies on the next episode. Till then, thank you.